Case Study 04, Centrality and Criticality, Why Betweenness Matters. All right, let's just jump right in and orient you to the exact engineering problem you're going to be tackling this weekend.
So imagine a severe storm hits your city. The Emergency Operations Center is scrambling, and they need to know right now which single transit station failure is going to completely fragment the network. Think about that for a second. It's not just some theoretical math puzzle. This is a concrete vulnerability problem, and engineers have to solve it before the crisis actually happens.
And that brings us to the core professional skill we're building here, which is the ability to measure. Because as engineers, we really have to move beyond just staring at a map and guessing. We need to actually quantify the exact load-bearing structure and pinpoint the choke points of these massive, interdependent systems.
But look, before you even think about touching any code, you're going to start on your sketchpad. The real thinking in this course happens on paper with your dark navy marker. The software, that's strictly there for verification later. So you'll start by just drawing a simple 10-node transit network. From there, you'll make two very deliberate choices. First, you're going to circle the highest degree node, and then you'll circle the highest betweenness node.
Now, doing this forces a really important core tension. You have to visually separate the busiest local hub, the node with the highest degree, from the actual structural bridge. That bridge is the choke point. It's the node that brokers the shortest paths across the entire network.
Once you've got that concept locked down on paper, you'll jump into the interactive Riverdale Metro exercise. Here, you're going to compare two very distinct stations. You look at Union Terminal, which is this massive, obvious hub with the highest degree, and you'll put it up against Ironworks. Ironworks is a relatively quiet station, but it connects two major clusters together, which gives it the highest betweenness. In the simulation, you'll actually remove each one of these stations one by one to see which one actually fragments the network. You'll monitor how the average path length shifts, and you'll watch the connected components literally break apart. But I'm definitely not going to spoil the learning check for you. You're going to figure that out yourself once you're in the tool. After that, you'll take these concepts and build out a pipeline. You can use R with iGraph or Python using NetworkX, whichever you prefer. You'll write a script to compute and rank compare 4 different centralities across a much larger 500-node synthetic network. Your main goal here is to systematically find those bridges that are just hiding in plain sight. Trust me, if you rely on the intuition you just built on your sketchpad, you'll do absolutely fine.
So what's the big takeaway? The crucial point here is dismantling a massive engineering misconception. The busiest node is rarely the most critical one to protect. Think about it. High-degree hubs usually have tons of redundancy built right around them. It's the high betweenness bridges, those invisible, load-bearing structures that actually break supply chains and take down power grids when they fail.
Okay, let's move to your final prompt. I want you to pause this explainer, pull out your sketchbook, and take a hard look at your drawn network. Circle the highest degree node, and then circle the highest betweenness node. If they happen to be the exact same node, add edges to your drawing until they diverge. You need to draw this divergence by hand before you move on to write a single line of code.